Hi again, Calc BC. Welcome back. This video is all about trying to figure out if series are convergent. Go figure, right? That's kind of our theme. In this video, what we're going to look at are two more ways to determine convergence divergence behavior for a series. And it's going to involve using two series. And so there are a couple of tests here that we're going to look at. The first one is called direct comparison. And as the name sort of implies, we just directly compare our series to another series that we have that we've already solved for whether it's convergent or divergent. What I mean by that is this. Let me get over to the whiteboard and show you. So for direct comparison, here's what we've got. We've got two sequences, A sub n and B sub n. And here's what we know. If we, let me grab a pen here. If we let 0 be less than A sub n less than B sub n. So here we go. And for right now, I'm going to say this is true for all n. Okay. We can tell two things here. If B sub n, the series B sub n converges, then the series A sub n converges. And this sort of makes sense, right? Because what we're saying is, look, B sub n is the sequence. Every term in B sub n is greater than A sub n. So imagine, if you will, if I were to plot these two out, fictional here, completely fictional, but if this is, let me change colors here. If this is B sub n, oops, just a drawing tool, there you go. And A sub n, oh, sorry, the green is B sub n. I gotta write that on here, B sub n. And A sub n are these pink dots. Okay, so that's A sub n. Well, if B sub n is convergent and A sub n is less than B sub n for every term, then A sub n has to converge. B sub n is sort of squishing it down there, because keep in mind, it's bounded below by 0. And so, yeah, this is a direct comparison to prove convergence. Okay, that's one of the things we can tell. Oops. There we go. The other thing we can tell, part 2 of the theorem, if the series A sub n diverges, then the series B sub n also diverges. Makes sense, right? Because if you think about that, right, now if we imagine the same kind of scenario, here's my axes again. Okay, this time, A sub n is doing something, like this. Come on. And B sub n is always greater than that. Well, there's nowhere for B sub n to go. Oops. Oh boy, that's ugly. Sorry. trying to write too quickly here. There's nowhere for B sub n to go other than to kind of go off and explode off to infinity. So it has to diverge. And so direct comparison is a really great way to prove convergence if you have a series that's greater than your series that we know converges. Or it can prove divergence if you have a series that's always less than your series. And it goes off to infinity. So let's take a look at an example here and see how we might use direct comparison. So my first series here, let's get my series up here, from 1 to infinity, of 1 over 2 plus 3 to the nth power. And I would like to know if that series converges or diverges. Okay. Well, just in looking at that series, I go, well, that's really similar. I mean, really similar to this series. See if you can figure out where this series came from. Ta-da. All right. Yeah, just get rid of the 2, right? Now, by adding 2 in the denominator, we know that the green series, we'll call that one a sub n, let's say, is always going to be just a little bit smaller than the pink series. We'll call that b sub n. So in this case, a sub n is less than b sub n. And what kind of series is this guy here? You guessed it. I'm taking advantage of the fact that's a geometric series. That's 1/3 to the nth power. So the common ratio is less than 1 in the geometric. Therefore, this series converges. Okay. So since, oops, 1 over 3 to the n is greater than 1 over 2 plus 3 to the n for all n, right? What do we know? This series converges by direct comparison. Yeah, that's exactly how direct comparison works. And so as we start to look at different series, we start to get an idea of, okay, so maybe we want to compare to a particular other series. How we come up with that other series, there's a little bit of an art form to that sometimes. Yeah, like this case, we compared to a geometric. Well, the geometric was sort of obvious when you look at 1 over 2 plus 3 to the n. The adding of 2 in the denominator eventually becomes pretty irrelevant as n gets really, really large. So we don't really have to worry about it. The the author has done it to us again in this section, and that's I don't know the nice way to say it. At the bottom of page 583, there is a note that is pretty important, because remember when I said at the beginning, I'm going to write this out and say for all n. Okay. Well, as you may remember from earlier, that's not always true, because the first finite number of terms we don't actually care about, right? Because any finite first 20 terms, 10 terms, 5 terms, 2 terms, 100 terms, whatever, that doesn't have any impact at all on the convergence or divergence of our series, because that will be a finite sum, guaranteed. So there should be a little, like, I don't know, it's a little caveat down here, a little note that says that actually um, the inequality only needs to hold for little n greater than or equal to some big N. So, whether it's the first 10 terms, it doesn't really matter, 20 terms, it doesn't really matter. Eventually, what we need to see is that our b sub n is greater than our a sub n. And then we can use either 1 or 2, depending on what we're trying to prove. Um, it does not need to be true for all n. And I just point that out because it's really important that we don't really care about the first couple terms. Here's a great example of a series where that's going to be true. Okay, so here's my series. Its n goes from 1 to infinity of 1 over 2 plus square root of n. Okay, and so our initial thought is to do kind of what we did in the last one, right? I mean, it makes sense, worked. So what's this series look like? N equals 1 to infinity of 1 over n to the 1/2 power. Oh, that's what kind of series? That's a p series. And look at p. P is less than 1. Therefore, this is divergent. But now let's check out the terms of our series. I'm going to call this one like before. I'm going to say, okay, you know, this is our a sub n, and this is our b sub n. Okay, and in the middle, n. Well, if n is 1, what's b sub n? B sub 1 is 1. Okay, but what's a sub n? 1/3. Uh-oh. Gosh darn it, that 1/3 looks terrible. I'm going to try again, guys. Um, if b sub n, right, is greater than a sub n, and b sub n is divergent, we don't know anything about a sub n. So yeah, this doesn't really seem to do much for us, but keep going. What about 2? All right, well, b sub n is 1 over root 2. Okay, a sub n, 1 over 2 plus square root of 2. Okay, a sub n is still smaller than b sub n. So obviously, this case, b sub n is always going to be smaller than a, or greater than a sub n, excuse me. And because b sub n is divergent, it doesn't tell us anything. So that comparison is going to fail. But compare to this. Okay, what do we know about the p series 1 over n? Okay, well, p is less than or equal to 1, which we know still means we have a divergent p series. Bear with me here, guys, because here's what's going to happen. Look what happens now. Okay, if n is 1, well, sure, we have the same thing, right? B sub n, this is an n here. It's just making me crazy. Okay, b sub n is 1. If n is 2, right, b sub n is 1/2. Okay, what happens when n is 4? They're equal to each other now. Oh, wait a minute. Okay. And once we get to like n equal, let's pick a nice perfect square, 9. Look what happens. A sub n, okay, well, that's 1/5. But what's b sub n? It's 1/9. And look, these first few terms, 1, 2, 3, okay, a sub n was always going to be a little bit less than b sub n. So we didn't have any kind of proof, right? For these top few terms, we had a sub n less than b sub n, less than or equal to, I guess. Okay, so the fact that b sub n was divergent didn't do anything for us because it was bigger than the term. But after 4, you can check this with a calculator if you want to go to decimals. Go 5, 6, 7, 8, 9 on up. From here on down to infinity, a sub n is now greater than or equal to b sub n. And b sub n is divergent. So this is where that little note at the bottom of the page on 583 is so important. Through the first 4 terms, n equals 1, 2, 3, 4, we didn't have any kind of proof that we could kind of look to from our direct comparison. But as soon as we get past 4, So capital N would be 4 in this case. B sub n is actually um, smaller than A sub n, and B sub n is divergent. That means A sub n diverges, and we have the answer to the question, what happens to this series, is divergent by direct comparison to this series over here. So even though the first 4 terms, the inequality that we want wasn't upheld, it doesn't actually matter. Okay. What matters is that after a certain number of terms, a finite number of terms, B sub n was the smaller one. And since it was getting bigger, it was blowing up, A sub n had to diverge as well. So that's one of the peculiar things that we see in our series here with the direct comparison test, is that sometimes we're going to direct compare to a series at first, and we're like, oh, we weren't able to get there. Like the first series that I used, 1 over the square root of n. So then we try a different series because maybe we see, oh, well, they still compare. And sure enough, after a point, we were able to get divergent for the 1 over 2 plus root n series. So there's a couple of examples there of using direct comparison, once with a convergent geometric series and once with a divergent p series to prove the convergence or divergence behavior of our original series. So yeah, what you're going to compare to is sometimes not obvious, but sometimes it is obvious, like in these ones, and direct comparison works really, really well. What if it doesn't? What if you're like, okay, I don't know what to direct compare to? You might try a different test, okay? Now, we're starting to develop this sort of catalog of skills for convergence, and so I want to make sure that we don't lose sight of the fact that the nth term divergence test is still probably the easiest one out there to determine if your series is divergent. Okay, if your sequence of terms doesn't go to 0, that's the easiest way to prove that a series is divergent. Unfortunately, like the ones I showed you here, the green one, the terms go to 0 on that. They also go to 0 on the pink term. Similarly here, the terms of the sequence, 1 over 2 plus square root of n, that goes to 0. Okay, that doesn't tell us anything. So we have to come up with a different way to prove convergence or divergence. And oops, direct comparison is one of them. Limit comparison is the other one. And so for limit comparison, what we're going to say is we're going to have 2 sequences. And we say, well, suppose we have the sequence A sub n that's greater than 0, and we have B sub n that's greater than 0. Okay. If the limit as n approaches infinity of the A sub n over B sub n is equal to L. Okay. Now what's L? L is a finite positive number. Oops, something like a B, there we go. Number. Okay. So if this is true, then the series have the same convergence divergence behavior. Yeah, so they're either both convergent or both divergent. Yeah, so what we need to do here is say, well, all right, let's see what happens if we have a series and we compare it using the limit to a different series. So And oops, that's right. Here we go. My example for this one is this. I have the square root of n over n squared plus 1. Okay. And now it's not quite as simple as before when we were doing like direct comparison, because I got the n's in the numerator and the denominator. So what I'm going to say is, well, if you look at that, if you ignore all but the most powerful terms in the numerator and denominator, then what this kind of looks like is this, right? I mean, because we square root of n over n squared, okay? And we know that this series here, that is a p series. More importantly, we know it's a convergent p series, because look at p is 3/2 greater than 1. So we want to somehow compare these two series together. Now, direct comparison would be a possibility, but I've got that square root of n in the numerator, and I really don't like the looks of that. So what I'm going to do instead is say, well, I know that they'll both have the same convergence divergence behavior if I look at the limit as n approaches infinity. And I'll take my first term, or my first series, and I'll divide by my next series. Now, obviously, dividing by a fraction, right? We're talking about multiplying by a reciprocal. And notice what would happen here, right? We'd get n squared over n plus 1. N squared plus 1, yeah. And now we can find that limit, right? That's a L'Hopital's rule. You could do L'Hopital's a couple of times, whatever. Eventually, though, you'll show that that limit is equal to 1, which is finite, which is positive. So by the limit comparison test, well, this series converges. There we go. Yeah, it's as simple as that. Okay, you just take the limit of the ratio of your first series to whatever series you've chosen for your convergence, and or divergence. I guess I should be clear here. It could be a divergent series that you're comparing it to, and that would be totally fine as well. That's totally appropriate. And as long as the limit turns out to be a finite positive number, they both have the same convergence divergence behavior. So there we are. That is direct comparison and limit comparison tests. Hopefully those made sense to you guys. And looking forward to class. I wanted to remind a few folks that if you are still interested, you had signed up to come to our live session on the 25th. And that is Kalel, Emerson, Blake, Josh, Ian, James, and Abby. So hopefully you guys can get there just a little bit before class time, like 5 minutes beforehand, so you can get signed in, get your temperature taken and stuff. And then I'll come up and meet you up by the front doors on the North Street entrance. So yeah, park in what you used to be the faculty lot. It will be the faculty lot again when we're all back in school. But for right now, park over there. Please don't park in the visitors lot in the middle of the circle. Try to keep that for people who are just stopping by quickly. Anyway, look forward to seeing you guys either on Zoom or in person on Friday. So have a great rest of your week, guys. Or not on Friday. I said Friday. I meant Thursday. Thanks.